Let us begin Chapter 2 by talking about the solar system. I believe it's in the ending part of Chapter 1, but it's most applicable to talk about it in Chapter 2. So let's see how the planets formed. So the origin of our solar system is about 15 billion years old. So it all started when the Big Bang happened. And galaxies are formed from space dust and gas. So it's essentially just space dust and gas come together. They're swirling. They have momentum. So that's what you see in this galaxy in this photo right here. And our particular solar system, the Milky Way, formed about 5 billion years ago. So there's a lot that's been happening out in space. The formation of our solar system is theorized by the nebular hypothesis. This hypothesis states that all bodies in the solar system formed out of a nebula. So on the right hand side, the image shows you a nebula, and in there, gravity compresses all of the materials, the space dust and the gas, into a planetary form. And when it makes this solid object, it's what's known as a protoplanet. So now protoplanet is basically just the beginnings of a planet, and once it fully forms, then it will turn into an actual planet. And so a nebula essentially is just made out of gases and space dust, like everything else in space, but it's just a huge cloud. So it's not like it's a planet. It's not like it's a fully formed solar system. It's just a big, massive, swirling concentration of space dust and gas. And it is mainly made out of hydrogen and helium. Those are the two main gases found in a nebula. So on this image on the right here, you can see the progression of the formation of a solar system. So it'll start off as a nebula where all the gases will be coming together. This nebula here has some rotation, and this initial nebula is three-dimensional, so it has gases and space dust swirling around in all directions, and eventually, once it comes to a very compressed state, it will be more disc shape, and it will have a very well defined center where you'll have like a proto-sun essentially. And then as this nebula continues to spin, and it will spin faster, and the materials will start to condense into protoplanets, which you'll see in steps in this third image there. So you go from A to B to C. So the image in C, that's where you have a proto-sun and a bunch of protoplanets occurring. And then in D, the image D, that's where you see a fully formed solar system where you have your sun in the center and you have your planets rotating around the sun. So let's talk about Earth. Where did Earth start? We know that Proto-Earth, which is the beginning Earth, was much larger than Earth is today. And this is because before an asteroid hit Proto-Earth, the Proto-Earth had much more material on it. And the material on Earth was homogeneous in composition. So that meant if you went from one side of the Earth to the other, you would see all the same materials throughout. Like on Earth today, you have your crust, and then you have your mantle, and then your core, and they're all made of different concentrations of minerals and material. But what ended up happening to Proto-Earth was this large asteroid hit Proto-Earth, and in that impact, it sent a lot of material into space. That asteroid itself crushed into small pieces, and some of it was left on Earth, some of it got shot up into space. And in this time, that material that got shot up started spinning around Earth and eventually created our moon. But a lot of material got shot up into space, so proto-Earth decreased in size to the size that it is right now. So let's look at the internal structure of Earth. Now this is after the solar system fully matured and all of the materials segregated into its different layers. And so what we're going to look at is density stratification. So each type of material has its own density, and whether it's denser or less dense than another material will determine where it's settled in the Earth's internal structure. And so density, remember, is just a unit of mass per unit volume. So that's how we quantify whether something is more or less dense than another material. And so on the left-hand side of this image, you'll see that materials were classified according to their chemical structure. And on the right-hand side, we have classifications for the materials according to their physical properties. So we will look at each one in more detail. So if we look at the chemical side, so the left-hand side, we have three different layers. We have the crust, which is at the topmost layer. That's essentially where we live at today. And then this crust right here is either made out of granite or basaltic material. So there's two types of crust. Granite type material would be land, continental material, and then oceanic crust would be basaltic, so anything in the ocean, any of the islands that were created there. The crust is about 20 miles thick, or 30 kilometers, and so it's not very thick in comparison to the other layers, and it's low density and made mainly out of silicate rocks. The mantle is the thickest, one of the thickest, is it the thickest? Is the second thickest layer, about 1,800 miles thick. It is high density and it's made primarily of iron, magnesium, and silicate rocks. And this particular layer is really hot, and this is where all of the lava that is generated on Earth comes from. And then we have the core. In this particular classification scheme, the core is just one layer. It's not separated into two. And this particular layer is just over 2,100 miles thick. It is very dense. It's made primarily out of iron and nickel and silicate. And this is pretty much where all of our really solid material ended up. So this is where the most dense material ended up as the Earth was spinning. So now if we switch over to the right hand side and we look at the physical properties classification, you can see there are 5 different layers in this classification, and we'll start at the very top with the lithosphere. This is essentially the crust on the other side, but it incorporates a little bit of the upper mantle. So this one is a little bit thicker than the crust at 62 miles thick. This one is cold, rigid, and brittle. So the crust is, you can classify that as that characterization. And the lithosphere is also where the plates for plate tectonics occur at. So they move on top of the upper mantle. Next, you have the asthenosphere, which is about 368 miles thick. This one is not rigid, it's plastic, so it has some flow to it. It's not completely fluid, it's not liquid, but think of when you try to melt plastic, you can kind of bend it a little bit, maybe like Play-Doh, for instance. You can bend it, you can move it, and it's not super rigid and solid like a rock. And this particular layer is very hot, so you wouldn't want to drill down to there. And then the next layer you have is the mesosphere, which is about just under 1,400 miles thick. This one is also hot, but it goes back to being rigid, so it's very solid. It lost all of its plasticity that the asthenosphere had. Then you have the outer core, which is about 1,400 miles thick. This one is hot, very hot, and it flows like liquid. So in this particular layer, this is where our magnetic field that protects the Earth from solar radiation is generated from, because of that iron and the magnetic materials that are found within the core. And then lastly, we have the inner core. This one is a little bit less thick. It's about 760 miles thick, and it is very hot down there, and it is rigid, so it went back to being solid. So it is no longer liquid. All right, and then lastly, let's go back to the crust types, and let's look at some characteristics of the different crusts. So the basaltic crust, which is oceanic in nature, it is an igneous rock. It is very dark colored. So if you guys are familiar with lava rocks here in Hawaii, that is oceanic crust. That is basaltic in nature. And it is more dense than continental crust. It is 3 grams per centimeter cubed. And it is it's not as thick. It's only 8 kilometers thick compared to your continental crust, which is made out of granite. It's lighter in color, and it's not as dense. It's 2.7 versus 3, which is not a big difference, but when you look at densities, it does matter. And generally speaking, the average thickness of continental crust is thicker at 35 kilometers, and that's to accommodate for the height of mountains. Generally, you don't have a lot of mountains in the oceans. It's generally very flat. And when we get into the chapter 3 for oceanography, we will be talking about ocean provinces, and that's where we will talk about the abyssal plains. And majority of the ocean is covered in abyssal plains. For zoology, we won't cover this very much at all. All right, so this was just part 1, and then we will look at part 2, which talks about plate tectonics.